We have broad objectives here. I'm going to spend an hour with you talking about certain issues that I've run into with tornado warning guidance and show maybe a little bit of new stuff. So it's going to be this case where I'm going to be pulling stuff, windows in and out. It's going to be rummaging through past cases, looking at other related things like that, but always with a similar set of objectives, and those objectives parallel the things that you need to know out in the field. And it's especially true with forecasting tornado potential probability intensity, that we have to look at the near storm environment, pre-tornadic signatures, and then we can look at other aspects as well, other parameters. And so it's a lot more than just radar signature strength there, although we'll take a look at some of these relationships with some candidate cases. But again, since we have an hour, I'm going to go ahead and review a couple of them here. And I thought some of them will be challenging cases and others maybe less so. And let me go ahead and maximize that. But there are some cases that we have, and some of them are from missed events, some from false alarms, some that are difficult with minimal lead time, and others. And actually, I'm going to go off this script and show you another challenging case from an unusual location. So throughout this, I'll probably start looking at calling out, asking questions. Keep on your toes. I may pick on you after I ask a question. Other times, I might just zoom through. So if that's fine, we'll go ahead. Now, some of these, when I'm talking about some of these events, they're all challenging. Some of them may be embarrassing to your office. And that's all right, because those are the ones that, we want to go and have an honest review and take a look at them. So, who was it from Wakefield here?
It's Alex here from Wakefield.
Were you around last February?
I was not, but I've heard all about it.
All right. Well, this is where we're going to start off. So,
good.
Let's take a look at this event. This is not a typical pattern for the East Coast. But then again, the Atlantic Piedmont sure gets its share of tornadic events, and you had a couple pretty good ones this year, didn't you, already?
It's been a pretty active year for us, yeah. We had eight tornadoes the other day, so.
Wow. Well, I'll tell you one thing. I got relatives that live in Virginia Beach, and there was a big one. I went right through Virginia Beach and ended 4 miles from their doorstep. But that one was well warned, and it was a fantastic job you guys did.
Thanks. So
let's go back to this one here and take a look at it. I got 60 knots of flow. This is at 925 millibars. And when you're talking 60 knots of flow at 925, you got one heck of a low-level jet. And you can see that just judging by the character of the system here, very early, it's actually third week in February, it's a strongly forced system. But again, a good direct feed right off the ocean with lots of moisture. And we look upstairs, and you got in excess of 100 knots of flow coming around the base of the trough as it's starting to lift out. So that's an absolutely intense flow right there for being at 500 millibars. In fact, you have actually up to 110 knots. So this is at 18Z. This is roughly, pretty close to the time that we're going to look at. We can see here that you have a system, the surface map, a couple things there of note. And, if you want to go ahead and chime in and see anything that you want, we're going to focus on the Wakefield area. And I think in that area, you might be able to see some things. Does anybody see any kind of features of note that you want to be keying in on? And I'd be willing to take volunteers. just by looking at this space plot.
This is Lake Charles. We see a dew point boundary there just to the north of the Wakefield CWA.
All right, so there's something off to the north right over here, maybe from the southern Chesapeake over to, it looks like Charlotte, huh? And some sense of maybe a damming event going down. In fact, that damming event goes all the way down to the North Carolina border, doesn't it? So the folks in the Blacksburg CWA are mostly free except for the eastern side of it. Anybody else see anything? All right, well, besides the fact that there's heavy snow in Lafayette, Indiana, this is a kind of cold front which we see often. Well, it's acting more like a dry line than a cold front. Very soft thermal gradient, initially right behind the boundary, but that's the kind of system, as we call in the old days, catafront. But now it's, again, still a catafront. But that's the kind of system there that's often associated with eastern tornado outbreaks. And if we look up, at let's say the effective bulk layer shear, you can see you got 65 to 80 knots. In fact, there's 90 knots down here, right in this area. And that's impressive. That's an amazing amount of bulk wind difference. So 90 knots over the effective layer, which I'm going to assume is going to be roughly about 5 kilometers in this case, because we see that there's minimal sin here, so we're probably entraining a lot of surface parcels. Got 1,000 joules per kilogram. Okay, with shear like that, you almost wonder if these things are just going to, any updrafts will just get shredded apart, and that's always a possibility. Effective layer SRH is pretty darn high, so that's 500 to 600 meters squared per second squared over most of the area. And you got, and this is the key thing right here, is the first guess storm motion. If there is one thing I see very often is that polygons tend to drift off course, and that's because of a bad initial guess, for storm motion. And so we want to be very clear, as to what your first guess is going to be after you correctly flag what kind of storm you're looking at. So this is right turning motion for right moving supercells. And so all of that yields a pretty high sigtor throughout the area right there. And of course it truncates wherever you have cold air, like along the lee side of the Appalachians. So anyway, I was looking at this and noting a couple things here, and I threw this together. So there's the wedge, so to speak, weak frontal boundary stretched across the tidewater, and the cold front to the south. So if we look at that circle in the tidewater region, we have a few candidate storms in that area. And I call it candidate for further investigation. We also see that this weak cold front is starting to light up as well. And so there's another area of candidates further southwest. Any convection in this whole area, though, could be construed as a candidate event. If I look at some RAP soundings, in fact, this is one from Fayetteville, down in North Carolina. This one is kind of interesting. When I look at this, it looks somewhat linear, doesn't it? There's certainly some helicity, 61, a huge amount of shear in the lowest 6 kilometers. But the interesting thing is you see that the angle of the shear relative to the low-level storm relative flow right here is fairly narrow. If I was to call it something, that would be, I think what we would call is a low critical angle. So, I need a better color than that, but hang on a second. There we go. So low-level shear, that's the low-level shear direction. Here's the stormlet of flow coming in right here. And that angle right there is called the critical angle. So I'll just call it C. And what you, ideally, if you wanted something where the storm was going to ingest all the shear, and all the shear would result in streamwise vorticity, then you'd want this angle to be 90 degrees so that the shear is perpendicular to the low-level storm relative flow. And that would mean that all of your flow coming in and all the vorticity along it, represented by the shear, is entirely streamwise. So literally, it's the spinning football being arrested straight upward into the base of the updraft. But in this case here, probably about 40 to 50% of that low-level shear is actually streamwise. And so the storm would have to work at it. They would have to either start turning more hard right to maximize the efficiency of getting streamwise vorticity, or the low-level shear would have to be so strong that the streamwise component, is still high. Now, in this case here, the low-level shear is, my gosh, let's see, it's 20 meters per second almost, 40 knots, which is very high. We like to look at stuff above 20 knots, so it's like twice above my personal threshold of really piqued interest. So, if we have roughly half of that, we're still right there, just about adequate, but not fantastic. So that's Fayetteville. Now we can move on here. And, okay. I want to point out a couple things here. I'm going to move forward a little bit. All right, hang on a second. To this one here. This is this is up here. Now we're talking about a sounding closer to Wakefield, northeast North Carolina. And at this point here, now we're looking at a situation where the critical angle is a lot higher. All right, so now looks like it's 60 degrees. Oops. So a lot more of this storm relative flow is going to contain streamwise vorticity because you're getting closer to that 90 degree threshold, and that's much more impressive. So I look at that and go, yeah, that's why a sickle-shaped photograph is so effective, because you can get a variety of storm motions, large variety around here. Storm could be here, or moving up here, or so forth, and you can have a lot of streamwise vorticity entering into that storm. The storm doesn't have to work at it to optimize it. It's got a lot of options. The only flaw that I see with this photograph is I see a layer here where the storm relative flow is a little bit weak because the right motion vector is kind of close to the photograph. And in that case, then a lot of precipitation may fall very close to the mesocyclone. And that could be a problem if you have a situation where precipitation could cause a lot of cold outflow and then suddenly gust out the storm. In this case, though, it's a little bit different because we're not seeing a lot of potential for cold outflow. The sounding's almost saturated. The low is 5,000 feet. In fact, the low is 15,000 feet. So it's very modest buoyancy. And in that modest buoyancy regime, I don't see a lot of dry air. And so that's a situation where storms could happily, storm updrafts, as long as they don't get ripped apart, they could happily coexist with precipitation dumping into them because of that lack of cold air source. Okay. So let's go over here. Now we're going to take a look at an MRMS plot. This is a 4-panel, and you got surface data right there. Temperature showing in the 60s, low 70s. And down here we have rotation tracks at the 0 to 2 kilometer layer. The most recent version of it is highlighted, and then the trails are kind of dimmed out a bit. Now, for you guys on the SBN, you probably only have access to the trails, but you can always go back and forth one frame and see what's the latest addition to them. And then on the lower left, we have the height of the 50 dBz above the melting layer, mesh and mesh trails in the upper right. So this is my situational awareness table. And I move forward in time, and I see the interesting thing that comes right out is, the capability of looking at a broad area and go, okay, what's my interest field, right off the bat, based on the environment and based on other things, non-meteorological things, or also what storm shows the strongest characteristics and so forth. So does anybody want to pick a storm here, at least at this point, and tell me what you think you would be interested in taking a look at?
The storm in the middle of the screen seems to have some pretty strong rotation tracks associated with it.
Yeah. So let's go ahead and zoom in a little bit on that one. So there it is. I was going to show this one anyway, so it's only appropriate. But you got that storm right now to the southwest. And a couple things I have on here. I have base velocity, upper right, lowest reflectivity scan, lower or upper left. And then we have KDP and ZDR on the bottom. And this is something that is starting to interest some people. Is the question of, can you tell if a storm has just got that look like it's accessing a lot of storm relative felicity and processing shear? And the theory is that if it is, there are two things that would happen. One is you start developing high ZDRs, which are primarily large drops, right along, let's say, the right kind of flank, so to speak, the forward flank, but sort of on the inflow side of that forward flank. And then we have a separation of large drops out. The large ones fall here near the border. And then you have smaller drops out there to the west. So that's one of the things that I like to look at. Now, if I was to look at the same time here, let me pull it up. Yeah. Okay, so I'm going to pull up the actual plot here and see if we notice the same thing here. So in this case here, if I put the center of the screen in each panel, let's say I put the center of the screen, I see that in fact I do get the ZDRs along this right edge. So that's an interesting thing. If I zoom out a bit, or let's say go up in elevation scan, I should see the ZDR arc disappear, and that's another one that's interesting to me. As I go up in the elevation scan, does anybody else see anything interesting? I'm roughly at about 13,000 feet above radar. Let's see, how about Roger, do you see anything else of interest, at least at this point?
You got me. Well, we're sitting here looking at the panel. I guess that is the lower left one, right?
Yeah.
Kind of between Yale and Louisville.
Mm-hmm.
I'm not sure what more.
I'll center it. There, let's see. It might help if I do this. Let me go ahead. Okay. Anything stand out yet, or you're gonna sit and wait for a bit and see what happens?
Yeah, I mean, yeah, we're conferring here. We say wait. Yeah.
Okay.
We're not feeling it.
Not urgent yet.
No.
All right. I'll move forward. Let me make this a little bit bigger here. If you want me to do anything with this, it's kind of hard for you to manipulate this, but I certainly could if you want. All right, so let's move forward a little bit and see what this storm does. Okay. Now we're we got sail scans running. So that's a key thing. And I think this is just the regular sails, not the Sails 3 version. So this is a little bit better. How about now? What do you think the change of that is? I'll keep picking on you, Roger, and your team, if you don't mind. And if you want, I can go up and tilt, cut a cross section or anything else.
On the tip of that thing? Can you raise it?
Yep. There we go. You notice the storm motion is so fast that every single tilt is going forward quite a bit. So I have to mentally extract that. All right. Anything of interest that you guys see? I'm at 10,000 feet. I'm lifting up to 15,000 feet.
VDR column. Yeah. There's definitely a hail there now, a ZDR column.
Yeah. There's a ZDR, a very well-defined ZDR column. Here's the melting line. Watch it shrink toward the radar past that ZDR column, and the ZDR column pokes well above it. And the KDP also. There's a KDP column as well, which is not surprising. And often cases, the KDP column disappears first, but this time they both do at the same time. If I step back, this is what happens here. Okay? Hopefully your screen updates as fast as mine does, but this is back 1854. And we move forward a little bit. And now we're at 1904. All right. So key things here is this sudden increase in reflectivity at 14,000 feet, mostly occupied by a ZDR column that goes up to 15,000. Finally tails off, before the beam reaches 19,000 feet. So that's what we're seeing. And then down below, I mean, this is one of these things where, I actually see a small B-were enclosed in there, which is another one that's really intriguing to me. And literally, you can see it right there. I mean, look at this. The one thing is, this storm motion is so fast that we're seeing an artificial tilt. So we can extract it out, but you can't extract the tilt out of this feature right here, which is very impressive. Okay. So if I looked at ZDR around that, you see the ZDR just completely enveloping the B-were right there. So, according to that, for you guys there, Roger's team, what would your action be at this point? I'm going to go down to the lowest scan.
Well, right now we're saying severe thunderstorm warning.
All right. Is that for hail, for wind, or both?
For hail.
For hail, okay. All right. Well, let's see what happens now as we step forward a little bit. Okay, we're now about 7 or 8 minutes forward in time. Okay. And we'll step up a little bit. And this is what we have. So that confirms, or at least I would think that might, just the appearance of that may support your idea for severe thunderstorm warning, I would assume. Okay, so given the environment here, is there anything else that you'd want to take a look at or consider communicating?
Looking at I'm interested in CC, and I'm interested in the is that the velocity pattern in the upper right, or what is that I'm looking at in the upper right?
Storm relative velocity. There's the CC.
Blow up that little area there. Yeah, right in there. Just blow that up so I can see the CC better.
Is that good?
Yeah. That looks pretty noisy in there, so I'm not really able to make anything out on that. This, velocity pattern, just a velocity pattern.
You want just base velocity?
Yeah.
Oops. There we go.
Yeah. I'm still liking that severe thunderstorm warning.
Okay. All right, there's a couple things here I want to point out too. Let's go back and look at ZDR, KDP. There's also some school of thoughts here that KDP is often dislocated from the ZDR. The ZDR arc, whose centroid would be displaced downstream of the centroid of the KDP. And that often indicates a storm also processing a lot of storm relative felicity. So we have a classic ZDR arc at this point. We have a very strong updraft to loft with a BWER. Certainly a severe thunderstorm warning is warranted in this case here. And down below, another interesting item is that, see right along in southeast or just ahead of this this concave region of sharp reflectivity gradient, you got very strong storm scale convergence here. So you got velocities, let's see, 31, 32 knots, then suddenly ramming into some slight inbounds right here. So outbounds into inbounds. And that's all embedded underneath. What we have here is developing circulation, 28 knots inbound, and then 9 to 10 knots outbound. So that's roughly about 30 knots delta V. Well, 30 knots delta V, that's the maximum that we see there, and that's roughly 12,000 feet. That's pretty high up. But down below, it's mostly convergence at this point. And so, if I was to look at a couple things here, let me pull up this chart. I'm going to pull this up. Okay, so this is in the TWG part, some of the reference guides. And if I actually looked at the probability of tornado at this point, Well, first of all, I need to look at low-level rotational velocity, and I can do that in knots. And if I did that, I need something that has rotational velocity, and I don't have anything down low. So, gee, this storm's not a candidate yet. I would need to look at something low level, and what I mean by low level is roughly 7,000 to 8,000 feet. So we're not seeing something yet that says, hey, let's pull the trigger. Now the question is where do you pull the trigger on something like this? I got an environment that's favorable for tornadoes. We looked at the sounding from the RAP. We can assume it's true. Strongly forced system. I think there's a moderate risk out for the day, and so forth. And yet, I had this storm, and, I got a ZDR arc. I've got a dislocation KDP from the ZDR centroids, which does have some suggestion that, those two items have a suggestion. This storm's processing helicity. It's actually utilizing it. It's got that look, and now we have strongly developing updraft here with this beware elevated ZDR column going up quite nicely. So everything fits the picture of an updraft erupting very strongly. But my velocity is still weak aloft, but I have decent convergence down here. It's about 35 knots of delta V down radial. But maybe you're not ready yet to pull the Tor trigger at this point. So we can move forward a little bit and see what happens. So I'm going to move forward, getting very close to the radar. Now I just, let's see, let's go, whoops, one more scan down. I can see the evolution. We started in 1912, now we go to 1918. And we still have no low-level rotation. We are literally 790 feet above the radar. And let's go ahead up and take a look. Loft. Still got a ZDR column. Essentially almost no change whatsoever. If we go up high enough to 13,000 feet, now that we're so close to the radar, I got to jump up a lot of scans just to get to the same altitude. And now I see, 34 knots of inbound, 10 knots of outbound. So my mesocyclone is strengthened by about 10 knots. But we're at 13,000 feet. So I consider that mid-levels, not really low-level. But everything else has got a really strong signature. Okay? And I still see a very, very stout ZDR arc along the forward flank here. So the thing that is interesting to me is the accelerated flow into the storm and an abrupt convergence. Convergence is not going away. And so this means already that parcels right down to the surface are being entrained into the storm. And if those parcels have a lot of streamwise vorticity, then the storm is processing all of that. So having said that, what do you think for Roger, for your team?
Go ahead. Well, we're looking at it, and based on what we're seeing, I mean, it's improving. We still have a severe thunderstorm warning out, though.
Mm-hmm.
I'm sure we have a possible tag for a possible tornado in the warning already.
Oh, you could have put one in the SVS, right?
Yeah.
Sure.
We're thinking.
All right, so
it's definitely looking better, but I'm not ready yet.
You're not ready to pull the trigger. Okay. All right, down to the lowest scan. Let's go jump one more. Now, let's assume elevated signatures are still good, but we're so darn close to the radar now. I'm just going to step forward one at a time, and you tell me to halt when you think you're ready to pull the trigger. This is kind of like saying when, stop. No, I meant when. I'm still filling up the cup. All right. Shall I go one more?
Yeah.
Yes.
Okay. How about now?
Oh, gosh. Can we go up?
Oh, I can go up as far as I
elevate up,
can.
'cause you're close to the radar. Can we elevate upwards a little bit?
I wish I pulled another radar, but we don't have one close enough. Okay.
Still not ready.
Still not ready? Okay.
Nope.
All right, let's move forward one step more. Unless I ran out of time. Oh my gosh. Hang on a second.
One more frame.
This is going to kill you, right? I hit the end of the loop. That's what happened.
Oh!
But
All right,
wait.
so how many minutes out are we? Just seconds?
Seconds? Minutes? How fast have you seen a tornado form?
A few minutes.
Hang on a second. I gotta yank that extra bit of time for you. Stand by. I can do this. I can do this. All right. Okay, we're at 1921, right? So let's go ahead and add a couple more. And I want you to consider all these things as we step forward in time. What would you be doing anything other than issuing SVSs and warnings at this point? What would you be putting on NWS chat?
Hold on now.
Go back.
Back that image up one.
Oh no,
I can't. That was
him loading it.
I'm going to go back to 1920. Oh my gosh. Here we go. Ready? There's 1923.
Now.
Now good.
You're getting cold. You're getting cold feet.
No, we saw the next frame, so.
Oh no, you didn't.
Yeah, too bad.
No, sorry. It looks just the same. You're still holding. Okay. There's 1929.
Come on, let's do it.
We're warning now. We're already warning.
You see a little shear there? Is that
Yeah.
Okay.
Yeah.
Let's go look aloft.
Oh yeah.
All right. So
There it is.
that pulled your trigger, didn't it? Let's go up here to where you see that nice inbound here, and let's measure that. So 34 knots inbound and about 26 outbound. That's roughly 35. How high am I? Oh, I'm at 6,000 feet. That's pretty darn high. If I go down a little bit lower, I can see that I got 30, 32 knots outbound and 25 to 28 knots outbound. So that's roughly the same strength. And at this altitude, I consider that low altitude. Now, what do I consider low altitude? Well, I'd like to think of anything below cloud base, but on this day, I think cloud base is at the bottom, at the ground. So about 1 kilometer. So if I have 32 knots and I look at my handy-dandy probability of tornado, let's say low-level rotational velocity, 32 knots, I'm a little bit under about 20%, at least at this time. If I look at let's say if I converted that to a skill score, that would hit close to the peak. The peak here is, anywhere from 30 to 40 knots. So I'm about there, about having the skill of the best discrimination between tornadic and non-tornadic vortices. So you still feel comfortable? You pulled the trigger, right?
Yeah, we did.
All right, that's good. Forgot to take a look at this cross-section here, but I wanted to see what it looked like in velocity. Oh, look at that, huh? So sloping mesocyclone, I cut it perfectly right through, so you can see both sides of it. Now you have to mentally kind of resurrect that, because of storm motion. But I think you get the idea. All right, let's see. As we go forward, what happened to that big jump? Oh, I know what happened. Okay. All right, let's go ahead. So I pulled up CC for a reason. Well, let's go up a little bit. See that? Right there.
Uh-huh. Oh, yes, we do.
All right, very good. By the way, that's only 5 minutes. Between these two scans, 5. Hey, actually, I wanted to get the perspective from Wakefield and what stories you heard. Who was that again? It was...
It's Alec here. We got a whole crew in here now, so.
It's always good to do it post-mortem, but the story of being there when you don't have somebody setting you up in advance, maybe you guys can relay your story on this one. This was a very challenging event.
Well, I mean, this is Mike too. I actually was I was moving down here. My car was in the repair shop in Beckley, West Virginia. But I don't know if any of us were actually. Well, Jeff, you were here, I guess, during the event.
Yeah, I was in my office. I was.
Yeah.
Well, I ended up here for a short period of time for other reasons.
But I think I think you hit the event pretty well. I sort of caught it on the tail end when you were talking, but. Essentially it's just a very quick, they were quick moving, first of all these events were this day. Second of all, the short amount of time that it descended, the mesocyclone descended. And third, the fact that it was so close, some of your conventional ways of looking at the tornadic circuit, the mesocyclone. I mean, at this point, you're essentially you're looking, not even looking at the meso, you're looking at the actual tornadic circulation.
So, literally the tornado, yeah.
Yes, you are. And so some of the stuff you have to some of the conventional things that you think about, you almost have to throw out the window in a way. Not throw out the window, but you have to sort of, but you have to think about where you are with respect to the RDA, and so. And so, looking at the 0.5, slice for, the pre touchdown was below, was sort of below cloud base. So you're having to really think about the actual storm evolution, the structure of the storm, and realize realize what you're seeing here. I mean, at that point, you're just seeing the inflow and the rear flank coming around. I mean, starting to come around at this point. Talking to the people, Jeff was saying that the inflow here at the office, the wind was just insane. I bet. Just insane at that point. And as an aside to this, you should see our hodograph. I actually have did a little talk. The hodograph based on our bad boom profile right before this was absolutely nuts. How much of a sickle type hodograph it was on this. Right about this time actually. I mean, it was just almost like a 90 degree hook in the hodograph. Sharp.
It's literally spinning footballs everywhere.
Yeah, I mean, very impressive, very challenging, very very impressive. I mean that inflow notch there that you see right there, underneath your square there. That was a really good sort of a first clue that bad stuff was cooking there with that storm. So
exactly, I think that's the key thing. I think hit a couple things is when you're so close to the radar, a mesocyclone isn't going to look like a mesocyclone. It's going to look like your whole velocity PPA pattern just dislocated off the radar, and you have multiple slices and gates in between the peak velocities. So you're literally drilling down, out here in Oklahoma, when we have these mile widers.
Yeah.
Although I've seen a few of those looking like that out in Virginia. We'll see sub-vortices inside of the tornado.
Right. Yep.
Just outrageous.
Yep.
So, yeah, this is a classic thing. This is a classic signature, pre-tornadic signature. Total convergence. But beautiful updraft signature right on top of that convergence. So it's just waiting for an excuse of any vertical vorticity to form, and then, off it goes. You got the meso, decent meso, but that updraft signature in the context of that environment with that convergence says, So,
Yeah.
yeah, that's a typical. I mean, that's a challenging one that can often yield misses when stuff develops right away, and now you have to go to those pre-tornadic signatures and see the stage all set up, ready to go.
Yeah, this is Andrew, lead forecaster here at Wakefield. I had a little bit of a different perspective of this event because I was looking after a friend's house in Waverly.
Oh, yeah.
Which got some peripheral damage from it. The tornado itself tracked about maybe 100 to 150 yards behind their house.
Oh, man.
And that, in my opinion, now I didn't do the survey, but I had driven around the track of it some. But since I had access to the woods behind their house, and it's in my opinion the tornado was at its strongest point when it went through that patch of woods as it was entering Waverly.
Oh, wow.
And that was actually prior to it reaching US 460, which is the highway running northwest to southeast from Waverly to Wakefield. So that tornado likely reached its strongest point, just within minutes after the signature you just had up there.
Oh, yeah.
And then it was probably actually weakening once you saw that broader CC pattern north of 460.
Huh. That's the amazing thing. So the delay factor in the TDS, you saw the debris go, but by the time debris is visible on radar, it's like the tornado is probably, could have peaked already. And so that's the problem with debris. Waiting for debris is a bad idea.
Yes, we had 8 tornadoes on Friday. Almost every single tornado we had this past Friday, the debris actually happened at or after the tornado lifted.
Yeah.
I mean, it was. Yeah. So you're right. You wait for debris, you're too late.
You're too late. Yeah. And especially if you're waiting for debris, to upgrade your tag to considerable or something like that. It's also that lag factor.
Yep.
Yeah, definitely. That's why I like, and there are several. Let's see if I can find this here. Yeah, this thing here. I think there are a couple cheat sheets here that we had, where we go, oh yeah, let's see, we wait. We want to go to considerable, so that's like moving over to this middle strong signature here, and we got rotational velocities 55 to 75 knots. And remember this, we put a criteria, this has to be within 100 kilometers of the radar, and it's a mesocyclonic tornado. So, given that, 55 to 75 knots of rotational velocity, it's like, yeah, that's worthy of a considerable, as long as you have a decent storm and it's a real signature, not some fake thing. But, the debris here, 10,000, if you wait for debris to reach 10,000 feet, you're in negative lead. You could be a potentially negative lead time. And, yeah, I agree. So it's good to confirm it, but, yeah, definitely otherwise I wouldn't want to touch it. I want to go ahead and bring up something else. There are 2 things I want to bring up, and we have to actually shut down after that. We went back to this other sounding where more of the vorticity was crosswise, so it's a little harder to get a tornado out of that, unless the storm really moves off the hodograph or something like that, or works on it, or something happens that we don't know anything about, which often does. But I run into this storm with this velocity pattern, and this one here speaks to something else that you have to worry about, and it catches a lot of people off guard. All right, so what am I talking about? Do any of you see anything here that says, oh my gosh, that's tornado warning territory? Let me see, the hint is, I just go ahead and look at this rotational velocity here, and it's all purple. Well, that's greater than negative 50 knots. And right next to it, I have near zero. 50 knots of, actually more than that. That's meters per second. That's 100 knots delta V. So 50 knots rotational velocity. So if I go to my cheat sheet here, to one of these, let me go back up to this one here that I have where I go 50 knots rotational velocity gives me better than 40% chance that thing is tornadic. if I took that at face value. Well, I'm roughly 46 nautical miles. I'm not far away from the radar, okay? Not very far away. All right? So, is that valid? Maybe the storm really is moving out the hodograph, and it really is sucking a lot more streamwise vorticity. I don't know. What do you think? Guys, we go for a tour on that one?
I'd want to look at a higher scan.
Dang it. You're one of those that wants to look at more data. Okay, what would you want to look for in a higher scan?
Vertical continuity.
Vertical, okay. Yeah. All right, so you're not ready to blindly pull the trigger. Yeah, and I'm glad you said that, because the one thing that you see here that sparks that this is not meteorological, or at least not real, is the sharp gradients that you see along the edges. This is not meteorologically looking, in other words. You notice this area of high velocity is in an area of relatively low reflectivity. In fact, you have this kind of patch of low reflectivity that's in the same shape as this anomalously high inbounds. And so it's also right next to an area of very high reflectivity. And this is a screaming signature of what we call side lobe effect, where the radar at a higher beam is, or let's say no, radar at this elevation, the side lobe that's pointing higher is slicing right into the echo overhang of this storm. And then, since the echo overhang is so strong, it's actually transmitting enough energy to overwhelm the very low reflectivities from the main beam down lower. And so it's pasting the echo right on top of the beam erroneously, and then is prime candidate to fool the forecaster who's not prepared to look for this and say, no, I'm not going to go for that one. So this often happens here when you have low reflectivity or high spectrum width. This is a candidate for that side lobing that goes on. Very important. Lots of tornado warnings have been issued off of these kinds of false signatures. So yeah, if you go up an elevation scan, you may see extremely high reflectivities, very high velocities up there. We saw the 500 millibar flow. It was like going 90 knots. That's pretty darn close to what that value is here. So anyway, that's a point to think about as we go through this. In fact, there we are. We're going up, just a little bit higher, and you can kind of see, again, those reflectivities where we have high inbound velocities, and this area is high reflectivity. Well, that's the overhang right there. All right, so think about that. Data quality is always ready to get you. Now let's see, what time do we have? Okay, 1:58. I think that's all the time I have to talk about, because I promised myself to stay inside of an hour. But I just wanted to point those things out because I love a good story. And when you're out there and you're sitting in the hot seat, you'll start acquiring your share of good stories, and it requires a sense of humility, because the atmosphere always finds out ways to try to trick you. And in this world of uncertainty, you may have some embarrassing moments. And to be honest, that happens to everybody here, even the best of them. Not to say Norman's the best of them, but they've been fooled quite a few times. And for some reason, I always seem to wind up walking into the office right when they missed a tornado. And then I sit there going, I guess this is the wrong time to have shown up, isn't it? So, I want to thank all of you that have participated, and I wish I had time to pick on all of you and kind of talk to you, but until next time we can do this again, actually next week, in which I think I will pick some different cases, different challenging cases, and I got a whole slurry full of whole bunch of them. So at this point here, Does anybody have any questions so far? All right. Okay, well, until next time, we'll talk to you later.